Hi, today we're going to talk about electric charge. We have two goals today. We're going to discuss the basics of electric charge, and secondly, we'll do some simple experiments and we'll try and explain them in terms of electric charge. As we see these experiments, it's nice to kind of keep this quote in mind. Any sufficiently advanced technology is indistinguishable from magic. Okay, so maybe we can explain these experiments we're going to do in terms of magic, but let's see if we can come up with some scientific explanation for them. And do you know who said that, by the way, this quote about magic? It was, in fact, Arthur C. Clarke, the famous science fiction writer. If you don't know anything about Clarke, it's probably a good idea to look him up. He was a very interesting fellow. Okay, so we're going to start just by doing some experiments. And the first one we're going to do, I'll describe it, and then we'll have a look at it on a little movie. So we'll have a nylon rod. It looks like a clear plastic rod. And we'll put it on a rotating stand. It won't be rotating, but it's free to rotate if it feels a torque. We're going to bring a second nylon rod close to the first one. We're not going to let them touch, but we're just going to bring them very close together. What do you think is going to happen? Well, what happens is absolutely nothing. Okay, so we'll try it again, but we'll prepare the rods first before we do it. So we'll rub both of the rods separately with a piece of felt. And then what happens is we get repulsion. So the rods don't touch, but they exert forces on one another. So it looks like magic, but maybe we can think up a scientific explanation. So try this one out for size. So we'll talk about charge transfer. Okay, so when you bring one material in contact with another, you generally transfer electrons, which have charges, which are charged, from one material to the other. And so that's what we're going to say happened in this case. Rubbing our nylon rod with the felt transferred electrons from one to the other. It gives the rod a particular sign charge, and of course the felt gets the opposite charge. And we treat the second rod the same way we treat the first rod, so it ends up having the same sign charge as the first rod, and we know that like charges repel. Okay, so let's see this in action. Okay, so here's our nylon rod sitting on the rotating stand. Okay, so bring the second rod close but not touching, and not a thing happens at all. Okay, so then we're going to try and transfer some charge here between the felt and the nylon. And the left end of the rod, where we touch it with the felt, should be where the charge is. So the left end of that rod is charged. We do exactly the same thing with the second rod, and it should be charged with the same sign as the first one. Bring them close, but don't touch. And you see there's a repulsive interaction between them. Okay, so it looks like magic. Looks like we have some magic wands here, but we can explain it in terms of charge transfer and then the fact that like charges repel. Okay, so let's try it again. This time we'll use rubber rods instead of nylon, and we'll use fur instead of felt. And we're going to see something very, very similar. Okay, so the two rubber rods initially do nothing at all to one another. So we'll rub them each with this piece of fur. So the left end of that rod should be now charged, and then the end of this rod should also be charged. We bring them close together, not touching, and we see again there's a nice repulsive interaction. And again, we can say some charge has been transferred between the fur and the rubber, and the two rubber rods were prepared the exact same way. So they should have the same sign charge as each other, and once again, like charges repel. Okay, so let's try a third experiment. This time, we'll take a rubber rod after it's been rubbed with fur and bring it close to a nylon rod after it's been rubbed with felt. So what do you think is going to happen in that case? Okay, so you might think that you're also going to see repulsion here. Maybe you're going to predict you're going to get attraction. Hard to tell which one is going to happen based on what we've seen so far, but feel free to make a prediction. And then we'll see it in action. So here we go. So these have not yet been rubbed yet, so nothing happens. Then we'll prepare the nylon one rod by rubbing it with the piece of felt, so it should now be charged. And we'll do a similar thing with the rubber rod. We'll rub it with the fur, and that should transfer some charge between the fur and the rod, and it should be charged. That rod should be charged now. Bring the rods close together, and now you see there's an attractive force between them. Okay, so once again, this looks like magic, but maybe we can explain it in terms of physics. And so what we know now is that the rods must have the opposite sign charge as one another, and because we know that unlike charges attract. Okay, so that actually fits just fine in our model of charge transfer and the fact that like charges repel and unlike charges attract. Okay, so let's have a look at this. It's called the triboelectric series, which is a pretty fancy name. In fact, that name comes from the Greek word tribos, which means to rub. So this is electrification by means of rubbing. And I've got a very small subset of the triboelectric series. Basically, any material you can think of has a particular spot in this list. And the higher up the material is, well, let me say it this way. If there are two materials you take from the list and bring them together, the one higher up donates electrons to the one further down. And so the one higher up ends up positive, and the one lower down ends up negative. Okay, so the first thing we did was bring the nylon in contact with the felt. Now, felt is not listed, it's not shown here on the list. It certainly has a spot on the list somewhere. It just doesn't appear on this particular subset. But felt, it turns out, is lower down the list than nylon. And so when felt and nylon are brought together, the nylon will give up electrons to the felt. And so the nylon ends up positive and the felt ends up negative. Conversely, when we did rubber and fur, well, fur is higher up the list than the rubber, and so the rubber ends up negative. It takes electrons from the fur, and the fur ends up positive. Okay? Now, if you think about where nylon is, nylon's close to the middle of this particular list. So we did nylon and felt, which is lower down the list, but we could have done nylon and, say, rabbit's fur. Okay, if we'd done that, nylon would have ended up negative in that case. So just because it's nylon doesn't tell you that it ends up positive. It depends on the relative position of the two materials in this particular list, the triboelectric series. Okay, so let's just cover some basics about charge, and I'm going to assume this is basically review from your years of education. Okay, we generally say there are two kinds of electric charge. We call them positive and negative. And generally, objects can gain a charge by either getting electrons, getting an excess of electrons, and electrons are themselves negatively charged, so getting more electrons brings with it a negative charge. Or an object can be charged by giving up electrons, and that will give it a net positive charge. And forces between charges can be substantial, for sure. I mean, we saw that with the movies of the rods. And we also want to go back and think about what happens, for instance, when you stand on a floor. Okay, so when you stand on the floor, the earth is trying to pull you down through the floor via the force of gravity, and the floor prevents that from happening. So in the past, what we said is that the floor exerts an upward normal force on you that exactly balances the downward force of gravity that acts on you. There's no net force on you, so you don't go anywhere. However, if you really get out your microscopes and look at what's going on at a microscopic level, then you'll see electron clouds in the soles of your shoes and more electron clouds in the top surface of the floor. And so what you've really got is repulsive forces coming from the electron clouds that are being brought close together. Okay, and that's really what the normal force comes from, the forces between charges. And other forces that we've dealt with before, we've called them tension or friction, things like that, really come about, again, from interactions between charged objects. Okay, two more things to tell you here. We're going to use Q, lowercase or uppercase, for our symbol for charge. And then we need a unit, and the unit we're going to use is the coulomb, capital C. It's named after a French scientist called Coulomb, who did a lot of work investigating forces between charged objects. Okay, so here's a little factoid about charge. Charge is quantized, which means what exactly? Well, anything that's quantized basically comes in indivisible little packets. Okay, so in general, we can say that charge, Q, equals N times E, where N is some integer, positive or negative, but some integer, and E has a particular value. It's the magnitude of the charge on the electron. And so here's E, 1.60 times 10 to the minus 19 coulombs. It's a very, very tiny amount of charge. But of course, an electron is a tiny, tiny thing. Okay, now, you may have heard about quarks. Quarks are a little bit special. They don't quite fit this quantization model because if you know anything about quarks, you know that their charges are plus or minus 1/3 of E or plus or minus 2/3 of E. And in fact, you take 3 quarks and put them together and make a proton, and a different set of 3 quarks put together makes a neutron. However, most things that we're going to deal with fit this model where things get charged by means of electron transfer, and then you're just transferring an integer number of electrons the whole time. So then we can say charge is quantized. Okay, one thing to keep in mind is the electron has a charge of negative E, proton has a charge of plus E. And do you know anything else that's maybe a common example, something you might use every day, that is quantized? I think a really nice example is money. Okay, for instance, the smallest increment, the indivisible amount, little package in the American system is the penny. So for instance, how much money do you have on you right now in your wallet, in your purse, in your pocket, wherever you keep it? It might be $5.43. Maybe it's $27.06, but you're never going to get fractions of a penny. Okay? Same with your bank account. You can break it down to the penny level, but you can't break it down any further than that. So you can't have fractions of a penny, you can't have fractions of an electron in general. So we'll go with charge is quantized. Okay, so here's a nice little table summarizing properties of the mass and the charge of some elementary particles, the electron, the proton, and the neutron. We've already gone over the fact that the electron and the proton have the same magnitude charge as one another, but opposite signs. Electron is negative, proton is positive. The neutron has no net charge. And mass-wise, even though the electron and the proton have exactly the same magnitude charge, the proton has a mass which is approximately 1,800 times that of the electron, and the neutron is just slightly more massive than the proton. Okay, but again, we're talking about tiny, tiny things. These are very, very small masses and charges we're talking about here for individual electrons, protons, and neutrons. Okay, here's another factoid about charge. Charge is conserved, and we're experts on conservation because we've dealt with energy conservation and momentum conservation, both linear and angular. Okay, so here we say charge is conserved. That means the net charge in a closed system is a constant value. And so let's try and apply that to this particular example here. We take 2 identical metal spheres. They're identical in every way aside from the amount of charge they have. So sphere A has a net charge of plus 7Q. Q represents a certain amount of charge. For instance, Q here might be E, or it could be 1,000,000 E, or 72,463 E, okay, something like that. But Q is some amount of charge. Sphere B has a different amount of charge. It's got a negative amount, minus 3Q. That's the net charge, again. The spheres are brought together. We're going to do this carefully, so no charge is transferred out of the system to us or transferred into the system from us. So we can apply charge conservation here. They're brought together, they're allowed to touch and then separated. What's the net charge on each sphere now after they're separated? And here's 5 possibilities. Okay, so let's analyze this in terms of charge conservation. So we're not allowing any charge to come in or go out of the system, our two-sphere system, so we can say charge is conserved. So how much charge did we have in the system to start with? The net charge is plus 4q, because we had plus 7q on sphere A and minus 3q on sphere B. It's important here that the spheres are metal, because electrons will flow very quickly and easily around the surface of the metal. And the other thing is the spheres are identical. That's very important too. So when the spheres touch very, very quickly, what's going to happen is the electrons are going to redistribute themselves. So you get a symmetric picture. Okay? So you have plus 4q worth of charge, and that splits evenly between the spheres, so that each sphere has a net charge of plus 2q when we're done. Okay, so you might want to think about how that happens. And in general, what we're going to do is just transfer electrons. So we actually transferred minus 5q worth of electrons from B to A. Now you could argue to me and say, well, B only had minus 3q to start with, so how did we get minus 5q to transfer? Well, you got to remember that minus 3q represents the net charge. Okay, so sphere A, sphere B, both the spheres have a whole bunch of electrons and a whole bunch of protons, and then we've just got some excess electrons on B to the tune of minus 3q worth. Okay, but the amount of electrons on B might be like a million q, and the protons might be a million minus 3q worth of protons. Okay, so you've got an excess of minus 3q. We really have tons more electrons to work with if we need them, so we can transfer minus 5q worth of electrons usually to A without any trouble at all. Okay, so we have 2q on each sphere when we're done. Okay, so that brings us to classifying materials, at least in terms of electrical properties. We talked about metals, for instance, when we did those spheres. And so generally we have three broad categories when we're classifying materials in terms of electrical properties. So there's one type of material, which is a conductor, and metals are good examples of conductors, and charge flows very easily around conductors. We've got an intermediate class we called semiconductors, and charge can flow, but not nearly as easily as it does through conductors. In fact, you usually use semiconductors in computers and electric circuits, cell phones, things like that, because you can control the amount of charge that flows. And then we've got a final class we call insulators. And nothing's a perfect insulator, but most insulators, in general insulators, are such that electrons flow much, much, much less easily through insulators than they do through conductors. Okay, so here's an example of when you'd use conductors and insulators together. A very common example is cell phone charger. Okay, so you want to recharge your cell phone. What do? You plug your charger into the wall. And then what's going to happen is you're going to have two wires that run from your cell phone charger to your cell phone. And you can think of these wires, if you want, as one wire carrying electrons from the wall socket to your cell phone, and the other wire carrying it back. Now, that's not such a bad way to think about it, actually. Now, what you don't want to have happen is for the electrons to transfer from one wire to the other wire before they reach your cell phone. And you also don't want to have electrons transfer out to you if you pick the wire up. Okay, you don't want to get a shock. So what you do is you surround each one of your metal wires with a rubber coating, so an electrical insulator, so you don't get a shock and the electrons don't leak out from one wire to the other one. It's not a short circuit. That would be a short circuit if we get wire-to-wire contact. Okay, so here's our final slide for the day, and try this at home. So we talked about doing some experiments, so feel free to try it yourself. So first of all, you need some kind of material that you will rub onto maybe something solid. Okay, so you can try your silk pajamas or your woolen sweater or your hair if you're going to rub a rubber balloon with your hair, for instance. So you can try maybe your silk pajamas or a piece of paper towel or something on a pen or a glass or something like that. So you can charge something. Well, how do you know if you charged anything? Well, a water stream is actually a really nice charge detector. So here, I'll demonstrate here. So take a very thin and freely flowing water stream here, smoothly flowing. I have charged this rod by rubbing it with felt. Bring it near the water stream, it deflects the water stream. It's amazing. Okay, so try that at home. See if you can set up a nice stream of water and charge something by rubbing it with your pajamas, your sweater, your paper towel, whatever you want. And then to see if your rubber balloon on your head, something like that. And then bring it close to the water stream. Well, why does that work exactly? So we know how to get the rod charged. In this case, I've just rubbed it with a piece of felt. Why does the water deflect that way? Okay, it was really seriously deflected. And if you know anything about the H2O molecule, well, you know that it's polar. Okay, it's got a positive side and a negative side. So when the positive rod, in this case, is brought close to the water stream, then all the negative ends of the molecules basically orient themselves to be close to the rod, and all the positive sides orient themselves to be further away from the rod. And so you get a little imbalance between the position of the negatives and the positives. The negatives are a little closer to the positive rod than the positives are. Okay? So you get basically an equal amount of charge, but it's just distributed a little bit differently on the water stream. And then you get the net attractive force between the positive rod and the negative ends of these polar molecules. That outweighs the repulsion you get between the positive rod and the positive ends of the molecules. So overall, you get an attractive force that deflects the water stream. So try that out at home and amaze all your friends. And you can explain it as magic, or you can explain it in terms of physics and charge transfer and the attractive and repulsive forces between charged objects. Okay, so that is all for today.